Hi, everyone. I'm going to talk about some of the different optoelectronic AFM methods that are available in our lab. This seemed to be the most popular option out of all the different possible topics I listed on the poll. I guess no one really wanted to hear about me rant about 2D Fourier transforms, except for Junshi, I guess. So maybe I'll just do that afterwards. Anyway, the general purpose is to provide a reference point for what methods are available, as well as how to run some of the other methods. So it's just kind of a brief walk through all the different techniques that we have. Well, not all of them, but some of them that we have in our lab, as well as what they have done in the context of photovoltaics in the past. So when I say optoelectronic scanning probe, what that means is an AFM, so that's atomic force microscope. Hopefully everyone knows that, plus light, plus electrical measurements. So what that means is you need a sharp metal tip, which we all, or metal coated tip, which we always use. All our tips tend to be metal coated, usually in chromium, platinum, or sometimes gold. You need a photovoltaic substrate. I guess it ideally should be on a transparent conducting substrate, although on the Cypher it doesn't necessarily matter. You need a light source, that's the opto part of optoelectronic, and then an electrical connection to the tip and sample, that's the electronic part. And then you combine those two and you get optoelectronic AFM, which is sort of a, I mean, it's kind of vaguely buzzwordy sounding term, but I sort of like it because I think it's descriptive. This is how it looks sort of at a rough schematic. At the left, you have some sort of bias or some sort of measurement rather between the tip and the sample. You're applying light. In our case, it usually comes from the bottom and is co-aligned with the tip. And then via that optical excitation, you can measure all sorts of things. So in the actual MFP3D system, this is sort of how the light looks like. This is kind of an old photo. Actually, it's a very old photo, but I still think it's nonetheless sort of vaguely descriptive. So up here we have our MFP3D head. Here's the sample. And then this yellow light follows the path of the LED. So in this case, you had a 405 LED. You shine it, it comes through here, bounces off a mirror, goes there, bounces off a mirror, goes off there, bounces off the 50-50 beam splitter that's in there, through an objective lens, focuses on the sample. And that's how you actually get the light into the system. So that's on the MFP3D. So before kind of walking through some of the optics that are actually there, I just wanted to briefly summarize what are the different techniques that I'll plan to cover in this PowerPoint presentation. So that's conducting AFM, photoconductive AFM, and then those are contact mode techniques. Then the non-contact ones, which are kind of Kelvin probe, EFM, a little bit of timer's law of the EFM, but don't worry, I'm not going to go sort of whole hog into that and discuss all the nitty-gritty damped-driven harmonic oscillator details. Then AFM, AM-FM, which is for stiffness mapping, and just kind of briefly, and then same with PIFM. Oh, and then intensity-modulated scanning Kelvin probe. I guess I should have sorted that in the list above Kelvin probe, but whatever. Things I won't cover that we can do in the lab that are much more complicated and kind of require you to be much more invested in fully into AFM is fast, free, time resolved DFM, and then G-mode Kelvin probe, as well as just like capacitive version of fast, free, which is kind of combining these two techniques. In any event, so before we get marching through some of these different techniques, how does the MFP3D system look optically? So here at the top, we have the AFM. So we have our AFM tip, our drive piezo. We have our laser, which I think is at 925 nanometer, but I actually can't remember. A top camera light. Then we have an active layer and then a bioelectrode. So this bioelectrode should be on a conductive, transparent conducting oxide. So that can be like ITO, FTO, whatever. And then on glass. So the optics on the bottom are it's actually quite complicated, or there's quite a lot involved. And that's because it's a full Nikon eclipse microscope in the FP3D. I'm not sure if everyone is fully aware. I know most of the older students know, but I think some of the younger students definitely don't. And so it's the same microscope that's actually, again, the confocal PL setup, for example. It just came with the AFM. Actually, we have two of them in the AFM lab. So on one side, we have three different kind of excitation sources. So one is a pulsed LED. So this is just an actual LED that's soldered to some wires to an external BNC, and it's glued onto this these little end caps that sit on the right side of the microscope. And so you can actually turn those on and modulate them if you want, or just turn them on just fully if you want, and those can shine through. You can also apply a halogen lamp, which we have. We don't usually use that very much, but it is widely available, and it's very easy, just plug and play. And it screws right onto the Nikon ports. There's also on the left side, through the left side of the microscope, there is a fiber port, so you can apply any sort of laser or any fiber coupled laser source into there. And by default, it's that 488 nanometer laser that's sitting on the cart right next to the new AFM, but you can do any other excitation. We've done 405 in the past. There's 660 nanometer laser. I actually don't know where that laser is anymore. I believe John or Mark probably borrowed it a long time ago. Probably Mark. He borrowed a lot of stuff. So, so I think that might be just sitting over in that other lab. But that I think is fiber coupled, and that can plug right in as long as it's FCPC coupled. So regardless of which light source you choose, it bounces into the AFM. There is a 50-50 beam splitter. You can also, there is a full mirror, so also 100% beam splitter, so 100-0, I guess, if you want. But by default, it's 50-50. It goes through this microscope objective, focus on the sample, and then some amount of light comes back, and through the port selector. By default, the port selector is on the eyepiece, so that way you can actually see what's going on. You could also change it to go through the PMT on the left side, and that goes through a set of filters. There's two 500 nanometer long pass filters and an 800 nanometer short pass filter. If you need to change to other filters, actually we do need to buy more filters. This is a good reminder if you want to use a 405 as an excitation source or whatever. But either way, these can go route into the PMT that's sitting there. That lets you do kind of this lock-in photoluminescence measurement. So that lets you correlate PL with your AFM measurement. And then I just made a side note here that the old MFP 3D microscope is actually quite underused. And it's a full microscope. So if you have some kind of complicated, cool optical measurement you want to try that couple with the AFM, please just let me know. That'd be fun to try. So the optical setup in the Cypher is slightly different, but you can accomplish most of the same thing. Except there, the laser has to be fiber coupled. In the MFP 3D, you could take off the couple and just free space couple it. You can't do that in the Cypher. So it's an external laser. It's fiber coupled. It plugs into this thing called the rainbow drive, which lets any fiber coupled wavelength in. So that's kind of why they call it the rainbow drive for, I guess, marketing reasons. That comes through this objective on the top and focuses on the sample. You do get shadowing from the tip. The light's not coming fully straight down, not just fully perpendicular. It's supposed to be at sort of a slight angle. That's my understanding anyway. So it's not completely shadowed, but it is shadowed by a good amount. We do have this bottom illumination stage that's on loan from Asylum. Actually, Alex Labuda, the guy from Asylum that built this, he asked me about it today, incidentally, just to see how it was going. And that has a white light LED kind of built into the stage from the bottom. And then you can apply just a filter right in front, which actually you have to take a hole punch and punch out these filters that he sent us and put those there. That's if you want to use a transparent substrate and illuminate from the bottom. But for the most part, you illuminate from the top, which means you don't have to have a transparent substrate. So if you're doing something that's actually on an opaque substrate, for example, if you're measuring photo excitation on silicon, like that's what Junshi is doing with the TMD samples, then you have to use the Cypher. So those are kind of the two optical setups for the lab. I should note that the reason that we have this PL setup, and this is an image from Giles and David's paper a long time ago, so we could do PL in the AFM that we already talked about. You can also do light beam induced current. So that's where you're shining a light kind of confocally across a sample, but instead of just measuring sort of an optical response, like what the wavelengths being emitted, or just even the sum of light being emitted, you measure the current. So it's kind of a way to do device measurements point by point, but you can use the AFM scanner to do that pretty easily and efficiently. And you can do a couple of other quite a wide range of things. And I should note that generally our PL measurements have been with this PMT, but I think you could probably use the ocean optics. I believe it requires some more careful alignment. There's a fair amount of light loss that was keeping us from doing it the last time we tried it, but I think in principle it should work just fine. So, and the excitation source right now, it's a 48 nanometer laser, but that doesn't have to be fixed or anything. That could be any range of systems that you want, hence this white light laser that I've been talking about. Here, I think I'm probably just going to skip past this. There's a couple of slides in here about how to actually try and line up samples. So you make a nice X, and then I go through this whole procedure here of how you actually scratch a box. I think this is probably more useful as a reference after the fact, because there's no reason for me to talk about this in some detail now. But this is how you scratch a box. The reason is so that if you make a box like this, you can take the sample over to the confocal PL microscope, or the PIFM or whatever other instrument you feel like, and then find this box. That way you can align two images together. And we've done this 10 trillion times in the past, and it works pretty reliably as long as you follow kind of this procedure in some detail written above. I should probably just write up an Igor procedure to actually do this, but it's not very complicated. I think you can just do it. It's fun. You probably won't screw up. So this is, so march you through some of the different techniques that are available. The first and most basic one for doing, I guess, electronic AFM or electrical AFM is conducting atomic force microscopy. So here you're applying a bias between your tip and your sample, and then measuring the current. It's very simple. So the tip has to be in contact mode in order for you to get current. And then the tip has to be connected to a current preamp that's built into the chip holder, though. So you don't have to worry about building that or anything. The resolution's sort of in the 10 nanometer range. It kind of depends on the tip radius. I should note that the tip does go bad over time because it's actually plowing into the surface when you're doing this. And also the bias voltage that you apply, in particular its polarity, plus the system energetic can determine if you're probing hole or electron current in the material. And if you're very careful, you can extract nanoscale JV curves, the current versus voltage. It's usually easier if you're trying to take many images at different biases and then stitch them together than to take JV curves at each pixel. And I should note that if you're trying to do this, it's probably best that you randomize the biases in that order. So like if you want to take, here, I'll let me draw that. If you're trying to take along from here to here, I would suggest you like maybe start here, 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 here at these different voltages and sort of do them out of order. That might be the best to prevent any sort of systematic biasing effects. But yeah, I don't know without actually having compared them systematically between doing it one way or the other. But either way, if you do several voltages in a row, you could stitch them together and form kind of nice JV curves. That's a little bit easier than trying to park at a single pixel and doing a JV sweep and then go in the next pixel doing that, because you get tons and tons of drift from doing that over the course of the image. All of these conducting AFM heads that we have, they're called the Orca head for sort of esoteric joke reasons. The other company that made their own conducting AFM, they called that module the tuna, and so Asylum's joke was that orcas eat tunas. That's the only reason they called it that. That's your fun side note for the day. The Orca holders can come in a couple of different ranges. So there's a 0.2 nanoamp per volt head. That's kind of our workhorse one. So that means the maximum current that you're going to measure is 2 nanoamps, because the maximum voltage it'll read is 10 volts that you can read into the AFM controller. There is one that measures 20 nanoamps. So that's a 2 nanoamp per volt head. That's for the MFP3D. I think on the Cypher, there's one that I believe measures 1 microamp, but that one's not. That part's not used. There's actually one of the heads. It contains 2 different preamps in it, so you measure 2 different currents at the same time. And one of them, I think, measures 1 microamp, and one is at 10 nanoamps. I have to double check. But either way, yeah, that's generally the range of currents that you're going to be measuring. What you can do with conducting AFM, well, you can measure all sorts of cool stuff. So in this particular case, this is one of these old fruit fly AFM or OPV samples, the P3HG PCBM. You can see at one polarity, you measure the whole current, and it's fairly uniform over the system. Whereas if you switch to electron current, you see all these isolated hotspots of connectivity, presumably through PCBM networks. So you do see very different holes versus electron networks. So in things like OPVs, where you kind of have these two different components that control your conductivity, you see this pretty readily. You can also use conducting AFM just in the dark on perovskites. So David Morman, old postdoc at our lab, did this, and actually really nice study. So some of you younger students might want to look at this paper. It's actually pretty easy to follow and well written. So there he mapped out the injected currents. This is in the dark on a MAPbBral, so it's a bromide perovskite sample. He also did PL, which is why having the PL in the AFM is really handy. And then he did kind of this manual machine learning method where he sort of masked off pixels based on the amount of PL. Like he found like all the bright PL pixels, went up to the current image, found all the average JV curves from those pixels, and took an average here. So you can see like here we have that region, which is very high current, is actually low PL. This region, which is comparatively less current, that's high PL. So what that means is these two things are actually anti-correlated. So where you're getting lots of PL, you're getting comparatively less current, and vice versa. And in this context, that had to do with contact effects from basically where you're getting deficient injection or contact to the, I believe it's P dot layer. If you had efficient charge injection, you're getting less PL because charges are being extracted, and vice versa. So that's some of the things you can do with just plain old conducting AFM. If you go one step further and you add light to the system, you have photoconductive AFM. So there you just shine light on the sample and co-align it with the tip. That can give you the photocurrent on the sample. Usually in the past with OPVs, we had to focus a laser pretty tightly on the sample for power density regions because the quantum efficiency is pretty low in a lot of those samples. With perovskites, you can actually get away with just an LED and you'll get photoconductive images just fine. Since the current's being measured where the tip is, I guess in some sense you have to worry about how much you're illuminating in terms of the diffusion length of carriers, I suppose, but that's sort of something that's dependent upon your particular experiment. So one of the nice things about photoconductive AFM is, like, even if you do it at 0 volts, you're measuring effectively, the short circuit photocurrent, right? And then if you compare those with, say, the regular conducting AFM, you get very different measurements. So again, this is pretty old results on P3HD PCBM, but I usually like bringing this up because it's a very nice comparison of all three methods on the same cell, and actually tells you something fairly informative, where in the photocurrent image, you get, regions that are very efficient as solar cells where you get high amounts of photocurrent. But there are also regions that are completely dead in terms of photocurrent. Whereas, if you look at the whole transport network, you're getting whole current everywhere. So that implies that if you're optimizing if you just optimize the whole transport material, that doesn't necessarily mean you'll get an improvement in the solar cell material, because we have a pretty, efficient whole transport material here in the sense that whole current is fairly uniform, but the photocurrent is not. So that was kind of like an interesting result at the time. And I think going forward, even for perovskite context, you probably have to care about the heterogeneity in the photocurrent. Indeed, you do see that the photocurrent is heterogeneous in photoconductive AFM on MAPbBral, for example. And people have done this. I believe Brian Huey's group did photoconductive AFM. I think that was on MAPbBral. I can't actually remember. This is I think it was an ACS Nano paper from a few years ago. Brian Huey's at UConn. So anyway, this is the topography on the left. This is the photoconductive AFM. You can see that it is quite heterogeneous, as evidenced from the distribution in the histogram of photocurrents down at the bottom. So you can actually use it on perovskites quite readily. I guess we haven't been doing it too much in the past. And it's quite easy to do this experiment since you don't have to do anything specialized. You just have to make sure your tip doesn't die during the course of the measurement. There's one thing to keep in mind, which is something I think people don't necessarily consider, which is that the work function of your tip doesn't really necessarily match the work function of the top contact in an actual solar cell material. That's because in the AFM, you want your tip to be fairly robust. So you want it to have like a deep work function so it doesn't oxidize like aluminum or whatever. You want something with a deep work function like gold or platinum. So those have fairly large work functions, but that doesn't necessarily match kind of the shallow work function of the material that you might have in a conventional solar cell material. So if you have like silver on top, that's a little bit different than having a work function of gold or aluminum from old OPVs. It's very different. So this paper from Barang Hamadani, who's at, I believe I think he's still at NIST, so maybe Lucas knows him. This compared work functions of this compared JV curves with tips of two different materials. So platinum, which is a fairly high work function, or deep work functions, maybe the parlance I should use, and this is a conductive doped diamond. It's a conductive diamond coated tip, rather. That's what CDC means in this case. That's actually a low work function tip material, and you see you get actually pretty different JV curves. Like these are both the same measurement, the same device, and then this is on an inverted device architecture, and you get pretty. In this case, you can see that there's quite a big difference between, like, actually, if you compare in the columns, you get quite a big difference in the JV curves that you measure, just depending on the different tip materials. So you have to keep that in mind. If you have like a large work function, bottom contact and a large work function for the tip, then you don't really have that much of a built-in field. So you might get very different actual physics going on. So you have to keep that in mind. So those are both contact techniques. So they're very simple to understand in the sense that you're applying a metal tip, you're pushing it onto the sample and measuring a current. There are a variety of other techniques that you can do. So one of these, this is just plain old electrostatic force microscopy in the AFM. So here's the schematic at the left. What you're doing is you're measuring a change in this cantilever resonance frequency. So cantilever oscillates at a particular frequency, maybe like 250 kilohertz or something. And you measure how much that frequency shifts. You apply a voltage and then measure how much that frequency shifts at each pixel in the image. And that depends on the electrostatic force gradient. That can be used for a number of different things, like measuring charge tapping, I think, dopant type and electrostatic dissipation. And the important part for a lot of you is that it's built into the software. It's actually quite easy to use. And one thing that Phil Cox, and he works at the test bed, and he used to be a student in our lab. He found that you can use this to map out the quality factor Q of the cantilever. So if you take a tune curve of the AFM tip, basically how wide this is at the full width half maximum, that's the quality factor Q. That's actually proportional to the electrostatic dissipation in the sample. So if you do something that changes or increases the amount of dissipation, so energetic dissipation. So for example, if you create a bunch of traps in the film, that would end up changing the Q. So you can map that out. And that's what he showed down here at the bottom. So here at the x-axis, he's changing the tip bias and sort of increasing the change in Q over time. And he's comparing the dark with the light. That's not as interesting as what I think the actual takeaway from this paper was. And if Dean is in the actual subgroup today, then he can maybe comment because he's on this paper. So here he parked the laser at different points on the sample to sort of degrade it for different amounts of time. And that actually shows up in the dissipation image. And so what this effectively is the amplitude channel from the EFM image, whereas like the frequency is the actual like electrostatic. As a typical EFM image is just a frequency channel. If you look at the amplitude, that actually lets you look at the dissipation, and it's really sensitive. So if you look here, you can even see this dot, and that's at 50 joules per square centimeter or something, some trivial amount of charge like that. And then obviously it's very sensitive it's very easy to measure, really high amounts of photodegradation. This frequency detection is useful for a lot of other experiments as well. So like John Marone's group did this on, they've done quite a lot in looking at organic semiconductor trapping, so pentacene and others. So this is from Justin Luria and John Marone. I'm not sure where Justin is now, but and then Lou Bruce and some others more recently have tried to use EFM to look at quantum dots. So this here, we're comparing the topography and then the EFM signal on quantum dots on the right. And then in this case, on the right side, this graph, they're sort of sweeping the bias and trying to see this amount of this total shift in this curve, both the curvature and sort of the shift in the kind of the vertex position, which should be the contact potential difference, kind of seeing where that shifts over time for photo on different quantum dots on their film. So that kind of leads into the next one that we could do, which is scanning Kelvin probe. That measures the contact potential or the work function, I guess. So if you combine that with light, that can be used to measure the surface photovoltage. And you could do this two different ways. You can do it in amplitude modulation mode that's built into the software. You can also do frequency modulation mode that requires some additional hardware, which we can do, and it requires actually some custom coding from our end. The general thing to keep in mind is that when you measure this, at least in the way we have it implemented, if you measure a higher CPD value, so that's more positive, that equates to a shallower work function, and a lower CPD value, so the more negative in value, equates to a deeper work function. The values that you get are relative unless you calibrate unless a known reference source. We do have graphite in the lab, like just a graphite sample hanging out, and I believe the work function is 4.65 EV for graphite. And that's generally pretty stable as long as you freshly cleave it, which is easy to do with a piece of Scotch tape. And so if you need to actually measure the work function exactly, or the contact, I guess change your relative contact potential difference into sort of an absolute number, then you have to take the same tip and go onto that graphite. And then ideally you want to do it a couple of times. So it's sort of tedious, but it's certainly possible. And then it's kind of for people's reference. I'm not going to discuss the method exactly down here, but I think for AFM students in particular, I kind of listed the method for AM mode below. You can do quite a few cool things. So your local research scientists, did some Kelvin probe on BAPI, so n equals 1 Perovskites, and found, there's a pretty big spatial difference. You'll see kind of a shallower work function here versus here, which is adjacent to the grain boundaries. Marina Leita's group has done a lot of, I think very recently, he's done some wavelength dependent Kelvin probe on MAPI. So you see actually pretty different results depending on which part of the wavelength, which wavelength range you're actually interrogating the sample with. And I think they were doing actually some time-dependent measurements as well. And she's done quite a few other Kelvin probe data. I believe she did the open circuit voltage mapping, where they have an additional feedback loop to keep it open circuit conditions. I believe that's her. And then also Bernard Grevin's paper. This is quite an old paper, but this is on P3HD PCBM, where they're comparing like the topography. This is the dissipation, and then this is the actual work function image from Kelvin probe. And so this is the measure they're getting. The one thing to keep in mind with Kelvin probe, though, is actually interpreting the data, especially under light, is quite complicated. So are you getting a photovoltage change? Is that due to band bending at the back contact? Is that band bending at the surface? Is it just due to the generation of excess carriers and they're just not recombining fast enough, et cetera? There's actually, for example, there's a pretty nice paper from Martin Kemrick and Klara Maturova. I believe that was a student. I can send a link later where they're comparing sort of Kelvin probe dynamics or the Kelvin probe contrast under light and in the dark on MDMO, PPV, PCBM solar cell. So again, an old OPV system. But the reason it's interesting is because you get this very heterogeneous vertical structure in the film of where the PCBM lies. And you get very different photovoltage behavior for each individual pixel, which is actually, so it makes interpreting Kelvin probe data, especially under light, quite complicated for a lot of solar cell materials. And sort of as a brief aside, to make sure that this is actually fairly exhaustive, I did go ahead and write up some notes for people about how FM Kelvin probe works. You do need an additional lock-in. The reason to do this frequency mode is that you have some notable advantages that you don't have these stray fields causing issues like you do in AM mode. You do generally get better resolution because you're looking at the force gradient rather than electrostatic force. And that's because you're trying to null out the phase. And again, kind of like on the previous slide, I did write out sort of the method in some step-by-step fashion for AFM students to actually try and go through at some point, or to keep it in mind. And then similar here is for when you actually want to set up the experiment. This actual diagram is printed out and pasted on the MFP3 chamber as well. I think that one's in color, or in better colors than this, but it's the same diagram. But going from Kelvin probe to another technique we can do, this one's called intensity-modulated scanning Kelvin probe, and it's something we haven't done in a while. One of the two people that actually did it is Micah, who runs the AFMs in MAF. So you can always go talk to him about it. So the instrumentation schematic, the top part is just the same as Kelvin probe. The bottom part is what's different. So in this case, instead of just applying a single static light source, like you might do to just measure photovoltage, where you just turn on a light and then measure the Kelvin probe image. In this case, you're modulating the light, and then you can, if you want, hold the device at a particular open circuit by applying a white light bias of a particular intensity. And as you modulate this bias, you're measuring the surface photovoltage. So when you measure surface photovoltage, that's an average measurement. So what that means is over the course of however long the feedback loop takes to actually settle on a value in Kelvin probe, that's going to determine your surface photovoltage. The problem is if you're modulating light, if it's at a very slow rate like this red curve, and as soon as you turn off the light, the actual photovoltage has enough time to relax. And then when you turn it back on, it reaches a value. Then when you turn it off, it has enough time to relax. So the average value is, this red line. If you're modulating at a very high frequency, like this blue curve, the surface photovoltage might reach a value. Then as soon as you turn it off, it might not have enough time to relax fully all the way back to zero before you turn the light on again. And so if you repeat this measurement, basically the photovoltage never goes back to zero because it's not, the lifetime is too long for it to actually relax. So then you get this blue value for the average that comes out. So what that means is if you're to take, say, the modulation frequency here and the photovoltage on the y-axis, at low frequencies, you'll get kind of a lower value because it can fully relax between the turning on and turning off. And then at some point, it'll saturate because it just won't be able to relax at all between the light turning on and turning off. So get some sort of characteristic curve that looks like this. And using some equations, you can actually extract the lifetime tau from that equation, from that curve. So the data takes a while to actually acquire, and it's very sensitive to noise and conditions. I believe when Gojang did this experiment, he was only doing it at night just to kind of avoid any other environmental factors. But you can do it. It is pretty hard to do it on perovskites for reasons I'll get to in the next slide. But it is readily available. The code exists, so you can do this experiment. I think it probably needs a little bit of debugging to get this to work with FM again, but that's a fun project. So one of the cool things about this FM-SKPM is you can measure the carrier lifetime in the AFM. One of the things that's kind of a problem, though, is the modulation rate that we can achieve on the LEDs in the lab is around, maybe at best 100 microseconds. I think realistically, you might be able to argue that it's 50 or 30 microseconds or something like that. And the laser is not that much better, actually, the TTL rate on the laser. That's part of the reason that David and I we're trying to shop around and see if this NKT laser will work, because you can achieve much higher modulation rates in theory. And the reason you want to do that, so if you extend this out to a much wider range, and you can actually, this y-axis, or this x-axis rather, to a much wider range, and you'll be able to explore kind of a wide range of materials, once it's saturated kind of longer times. So that's kind of the, especially for perovskites, I think that's probably the more interesting part. And you can, and then also if you have the wavelength dependence of the NKT laser, then that gives you a lot of other options. But anyway, this FM-SKPM exists, and it's something that I think we could stand to be doing on some more of the perovskite materials, especially if you want to look at the influence of, the work function of different HTL and ETLs, I guess the HTL in this context, on the material. Then you probably want to look at the lifetime. You can try and measure that in the AFM directly. And it's a hard experiment, but all the hard work of actually doing all the coding that's already been done. So the last bit I wanted to go through is just kind of briefly is time resolved EFM, because I think not everyone in the lab knows how that works. So when I talked about EFM earlier, which is just standard, if you apply a voltage and measure the frequency shift, if instead of just measuring the frequency shift, you measure how long the frequency takes to reach how long the frequency takes to shift, then that's time resolved EFM. And actually people did this quite a long time ago. This is the Schermeisen group did this, I believe, in the late 90s. And then David Coffey and David Giger, did this on solar cells. This is that image down the left. This is PFB FABT. And then they showed actually a lot of really cool stuff, in particular that trEFM is very predictive. So what that means is if you have something with really lousy EQE, you're going to get a low trEFM rate. And if you have something with the higher EQE, you'll get a higher trEFM rate. And so that relationship's monotonic. And so that also means that if you look at a trEFM image, then I can sort of say this particular pixel, well, that's lower EQE than this one, which is a much higher EQE. It's also non-contact. And the other thing about it is that the time resolution tends to be limited by your feedback loop bandwidth. There are lots of ways to get around that, but they're quite a bit more complicated. And that's sort of the thing that I work on a lot. So I won't discuss that in any detail in this presentation. But if you do get around that feedback loop limitation, you could take images and other things. So this is another OPV system. This is MDMO PVV PCBM. This one is actually BAPI. So that's the perovskite that I was looking at on Kelvin probe a few slides back. So this is the time resolved EFM image at the bottom, and that's the topography at the top. And you can see there's a big spatial dependence of the charging rate on BAPI as well. And I was actually kind of proud. This image took quite a lot to actually acquire, but it's kind of the first time we were able to successfully do this on perovskites, which is pretty neat. So you're able to do this technique on some other systems as well. And Junchi is trying to do this on the TMD samples as we speak. One of the nice things about trEFM is that it tends to be predictive. So this is Phil's data left, where if you look at the wavelength dependence of the EQE, this is on MDMO, PPV, PCBM, I believe. So as the EQE goes down, that's in black, so that's from the device measurement. The charging rate also goes down. Like I said, there's kind of this relationship. That trend between the two is monotonic. And then Obadiah, who is I believe he's at the University of Colorado. I'm not sure if he's actually at NREL, but either way, I think he does almost all his work at NREL. He was comparing photon dose. So he was intentionally degrading films and then measuring the time resolved EFM rate and comparing that with EQE. So those both correlate. So you can actually, as the EQE drops almost to zero, the time resolved EFM rate also drops as well. And then of note is that the surface photovoltage is considerably less sensitive. So while Kelvin probe is actually quite popular for measuring very difficult measurements at low photon doses or low changes or small changes in EQE, surface photovoltage is nowhere near sensitive enough. So the other two techniques that I think are left is just stiffness mapping and PIFM. Stiffness mapping is also built into the AFM software. I should say that our lab historically, this is probably, honestly, this slide falls a little bit outside the title slide, which is Optoelectronic AFM, because it's not an optoelectronic measurement at all. But I guess I already included this slide, so I'll already talk about it. So this lets you measure the stiffness and the Young's modules of the sample in a tapping mode geometry, which is kind of nice. We don't usually measure stiffness that much. The OECT people probably need to be doing this more. So this is one of the things that Lucas and I were looking at in that original paper with P3HT. In OECT, we actually do care a lot about how the crystallinity and sidechain packing, et cetera, affect ion uptake in the material. So we probably should be looking a little bit more at how the stiffness relates to the distribution of other properties in those films. This is readily available in the AFM software. It's quite easy to do as long as you take a 75 kilohertz cantilever. You want to be doing this on the Cypher. I think you can't really do this on the MFP3D that easily. But this is the topography on the left. And then if you'll get a frequency image, and then depending on if you've calibrated the system or not, you can get a Young's modulus image. On the frequency shift at the second resonance, if you see lower frequencies is a comparatively less stiff region of the film than higher frequencies. And so we did this with OECTs along, a couple of years ago to show that these two factors related to how easily ions could get into the film. So that's something you can do with stiffness mapping. The last slide is about PIFM, and I just wanted to include this one summary slide so that people can come back and actually, if nothing else, grab this instrument schematic at the top to use in whatever image you want. So it's a tapping mode technique. This is the molecular vista system. So that's the other one that's sitting in the MAF. If you want to use it, you have to ask me or Micah, but we'll train you. I should note it's free for grad students to use, so you should use it. It works quite nicely these days. They've fixed a lot of the things for us over the course of the summer. Micah's done a really nice job on actually bringing that up to speed by fixing a lot of the other bugs, and he uses it quite pretty regularly these days. So in this case, it measures the photothermal expansion or the photoinduced force, depending on who you talk to, from an IR source on a sample. And by IR, I mean that the laser ranges from 800 to 1800 inverse centimeters. So that's something like 12.5 microns to 5.5 microns, give or take. So in some sense, it's like a nanoscale FTIR measurement. You don't exactly get the same spectra as you do in FTIR, but you should get reasonably close. And it's ideal for samples with really strong vibrational features that are in this range. That's organic molecules. And that includes like methylammonium or formamidinium, for example. Inorganic components you probably won't see because they generally fall outside this range. Some things that are really easy to see are carbonyls, tend to show up really easily in the PIFM. Other things that show up if you're doing OECT measurements or anything with ion conductors, PF6 is very easy to see in the system. And that's actually Connor's the first one that found that out in our group, I believe. But if you do that, you can actually, and if you do this carefully, you can get a wide range of different things. This is an old data set that I believe I showed. So this is this polymer called DPP-DTT mixed with polystyrene in this weird composite. You can ignore the top row, but the bottom is all PIFM. So this is at two different wave numbers, so 1492 and 1668. And you can see that in one particular wave number range, you get kind of this polystyrene everywhere. And the 1668 corresponds to a carbonyl stretch that's in DPP-DTT only. And you can see how that forms this more nanowiry structure. So you can actually use this to map out different compositions in your material. It's very dependent on the tip, and your tip can get ruined very easily in the system. But fortunately, you can just use any of the standard tips that we have and get pretty reasonable data. So it's a pretty nice microscope for doing this nanoscale chemical mapping. And I should say it's quite unique relative to other institutions. Most people don't have an AFM-IR system, or if they do, it's generally underutilized. So that's something, especially perovskite people, if you have an organic cation, if you have an all inorganic perovskite, this probably won't help you. But if you have one with organic cations, then there's probably something to be gained from the PIFM. And I should say, the reason I'm mentioning this is that the system does work quite a lot better now than it did last year or the year before. If you did initial perovskite work like a year or two ago and you found it very frustrating, you generally should get probably better data now if you're to try and use it. It's not a panacea, it won't solve everything, but I think it's a pretty good microscope. So with that being said, I don't actually have a concluding slide, but that's hopefully a fairly long tour of all the different techniques that we have available in the lab. And if you want more details or anything like that, please just let me know. And with that, I'm going to save this on the shared drive, and then people can go back and look at some of the slides I skipped over, such as how to make an X and things, and how to scratch a box and things like that. Okay, thanks. How do I stop recording?